So tonight we have our first 8 lightning talkers, and it's kind of a surprise. You'll find out as each person comes up what they want to talk about. So stick around because there's all kinds of different, diverse. The best thing about this whole week is everything's so different. So first we have Julian Smith. Where are you, Julian? He was here. There you go. Come on up. Julian, I like this, author of an unsuccessful proposal to add multi-methods to C++, 10 years ago and still carries the scars from writing a crude C++ parser for the example implementation. But now he's co-founded Undodb Software, and he works on record and replay debugging technology. So you have 15 minutes on this clock. All right? Knock him out. That mic is live for you.
Thank you. Great. I can't see it on that screen.
It's not there, but it is there.
Okay. Oh, it is now.
Step out of faith. There you go.
Great. Thank you, everybody. Yes, I work for Undodb Software. As well as making lanyards, we write a reversible debugger. So I'll just give you a quick demo of what a reversible debugger looks like. So here's a very simple program. Thank you. So we're going to run it, and it'll stop at the beginning of main. Here we are at the beginning of main. And we can step forwards in the normal way, and you can see these values here changing as we step forward. And because it's a reversible debugger, we can go backwards. So I can click this button here, and we go back. And you'll notice these values restoring back to their original values. And in particular, if you look at Z, that contains a sort of a random value when the program started up, and that's been restored. So you can go backwards and forwards as much as you like, and that's a reversible debugger. So we've been going sort of maybe 9 or 10 years. It was founded by me and Greg Law, and we've got 10 people now in Cambridge, and me in Oxford in the UK, and various customers, as you can see on that slide. So reversible debuggers, well, obviously they let you step backwards as well as forwards. I guess anybody who's programmed a compiled language will have used a debugger at some point, and you've had the problem where something goes wrong, you put it in the debugger, you stop somewhere, you single step forward, and you single step too far, and you want to go back again, go back into a function call. Debugging is really frustrating. So with a reversible debugger, all those problems go away, because if you go a bit further more than you want, you just go back. And you can go backwards and forwards as many times as you like and home in on a bug. So I'm going to give a couple of very, very simple examples today, but actually our software is used on very complicated software projects with massive programs, with loads of memory, lots of shared memory, all sorts of heavyweight sort of programming. And one thing should be clear, it's for compiled code on Linux. It doesn't work on Mac OS or Windows. There's an interesting quote, which we particularly like, from Koeniger and Pike, which is about the reverse debugging, which is it's all about solving a bug is like solving a murder mystery. You've got the end state, you've got the dead body. You don't know what happened before the body was killed. With debugging, it's the same thing. You've got the end state, you've got a core file, or perhaps if you're in the debugger, you've got the state of the program right now. You don't know what happened in the past. So Undodb gives you a rewind button, and we think it's like CCTV for your code. So I'm just going to give you a slightly more complicated example, just to give you an idea of how reverse debugging can simplify life. So we've got a very toy program, got a cache. It's a cache of the square roots of 8-bit values. And there's 100 entries in the cache. We've got a function that, and have to forgive me for going a bit quickly here because I've only got 15 minutes, a cache calculate function which, given a value, it looks it up in the cache. If it's there, it returns it. Otherwise, it populates a couple of adjacent entries in the cache and then returns the square root. So that's obviously a very simple toy example, but it's a sort of character that we all use in programs with cache values in some sort of data structure in memory. And this has got deliberate error, but obviously normally we don't have deliberate errors, but errors in this sort of cache sort of data structure are not uncommon. And indeed, this program will be running a test, runs forever until it either assert fails or carries on forever. And if I run it, here we go, we've hit that assert. So basically, we've called cache calculate, it's returned a value of square root of 0, but actually, it should have been 15. We're trying to calculate the square root of 255 in integer arithmetic. So cache calculate has done the wrong thing. So what we can do with a reverse debugger, we set a breakpoint there. We're deep inside assert at the moment. We can go back to that breakpoint and then go reverse step upwards. And at this point, we're going to reverse step into cache calculate. And here we go, the end of cache calculate. We're going to go back and see what's happened. Okay, so it looks like cache calculate has found the value in the cache, and it's returning from the cache. So what's the value? 255. And I is 90. And because I've run this demo before, I already have it pre-set up. So cache element 90 says that the square root of 255 is 0. Well, that's clearly wrong. So what do? Well, normally you'd be a bit stuck because that happened in the past. That cache, that element in the cache was corrupted. We don't know when. We don't know what code did it. But with the reverse debugger, we've got a rather neat little trick. We're going to set a watch point on cache element 90 value and add that. And then we're going to run backwards. And we're going to run backwards to the time when that cache element was modified. So reverse continue, there you go. And here we are back in cache calculate in the past. And, well, let's see what's going on. Aha. Well, value 2 is -1. So we know something's gone wrong. One thing you can do if you want to is you can actually look at cache element 90 getting corrupted. At the moment it has 40 and 6, which is in an integer arithmetic is okay. If we step forwards, you can see it getting corrupted. It now contains 255 and 0. Okay, so, well, some of you might have spotted what's gone wrong, but just for fun, we're going to try and find out why has value 2 got value of -1. So we'll set another watch point on value 2. And we'll run backwards. And not surprisingly, it's in this loop here. So what's happened is value itself is 0. We're looping from value -1. So this bug is that the loop is trying to find the square root of a negative number. So square root has returned some ridiculous value, and it's corrupting the cache. So hopefully you'll be able to see that this sort of technology is kind of useful in this sort of problem, but more generally, this sort of, especially backwards watch points, are just so powerful. I guess one of the key things about Undodb is that we've worked very hard on performance. Obviously, in the toy programs I've just been showing, it doesn't really mean much. But actually, even with big programs, we're pretty good at speed. So we don't store the result of every single instruction, because that will be gigabytes of data per second. So what instead we do is we know that computers generally run deterministically forwards, so we make snapshots. And then to go backwards, we actually go back to a snapshot and run forwards, replaying any non-deterministic input. So if your program, when it ran the first time, read some data from a socket, we store that data so that when we replay, we can replicate what the original read did. And we do that for all system calls. Because system calls can modify memory in all sorts of different ways, and basically we know about every single system call in Linux, and we store and replay what they all do. We also have to deal with thread switches and signals and shared memory and all various things like that. And as an indication of the speed, GDB has a sort of thing called process record, which is a very simple reverse debugging system. but it isn't really comparable, as you can see from these timings. So this is running gzip on a 16 megabyte file. As you can see with Undodb, it's about half the speed, and it uses some extra memory. With GDB, it takes all day and it takes gigabytes, tens of gigabytes of memory. So if you had a bug in gzip, GDB process record, unfortunately, it's just not helpful. With Undodb, you can actually run it in the debugger, run it backwards, and figure out what's gone wrong really easily. I won't bore you with this. Well, actually, maybe I will. The thing about debugging is we all think we don't need to do it. And we all tell ourselves we're pretty good at writing code that doesn't have bugs. I certainly know I write code with lots of bugs. The demo I gave earlier on, Greg asked me to write the code because he thought I was good at writing bugs, I think. So, yeah, we all write bugs, and it takes enormous amounts of our time. It takes enormous amounts of money in our wages. It affects the reputation of the companies we work for in ways we don't really want to think about. So any improvement in how you can fix bugs and address the problems is really, really important. So to that end, a reversible debugger, I think, could make quite a difference to many, many people. So I'll just sort of finish up now. So we work on unmodified Linux. We don't need any kernel patches. We don't need any recompilation. We only do the reverse record and replay engine. We don't do the symbol lookup and things. We leave that to another debugger. In the example you were just seeing, that was GDB with a KGDB front end. But we work with the TotalView debuggers with a replay engine in TotalView and in ARM's DS5 debugging suite. So we don't get involved in the symbols. So you don't need to recompile anything. As the slide says, we work on thread signals, shared memory, all that sort of thing. So as well as the first example of where we're good at is effects manifesting themselves a long time after a bug. That's sort of the cache example. It's also very useful when you get a problem that only occurs very occasionally. If a problem only occurs every, say, 1,000 times you run the program, it's very difficult to debug using a normal debugger because you run it 1,000 times, you eventually capture it in the debugger, then you run it, and you think, oh, I meant to set a breakpoint at that function, and then you've got to run it another 1,000 times to kind of capture the bug again. With a reversible debugger, you capture it once, and you're done. You can go backwards and forwards as much as you like. Also, you can investigate unfamiliar code bases, figuring out who called this, why did they call it. You can go backwards and forwards. It's really, really, really useful. And aside from that, as you saw, we had watchpoints you can attach to existing processes, and it's basically a replacement, a command line replacement for GDB, so you can use it in Eclipse or Emacs or whatever other debugging environment you would like to use. And then just finally, we have a new product which we're getting close to releasing now called the Flight Recorder, where you link our engine into your code, ship it to a customer, it runs on the customer site, and at the customer's control, they can tell it to start recording. Then if it goes wrong, they can save the recording to a file, they ship the file back to you, it might be quite big, you might need a few DVDs, and then you can use reversible debugging on that file to figure out what happened at the customer site. So you don't have to reproduce bugs. You don't have to depend on customers giving you a detailed example of how to reproduce what they did to cause the problem. So that's our technology, and it's quite exciting. I hope you found it interesting. Thank you.